Two big questions in calculus are how do you find instantaneous velocity and how do you find the area of exotic shapes. We can approximate the area by dividing the region into rectangles. The area covered by the rectangles can be expressed as the sum of the area of the individual rectangles. Sigma notation provides a shorthand expression for the sums. So with sigma notation, it's just a way of compactly describing what we're adding up. I mean, what will we use to find the values without always writing all the values down. And it allows us a way to find different values. Right, so let's take a look at what sigma notation tells us. All right, so here we have an example. We have the sigma, and it would be the sigma is the sum of, in this case, it was all the values of from k equals 2 to k equals 5, substituted into our formula 3k plus 1. Right? So in other words, the variable at the expression there at the bottom of the sigma tells us just what variable we're using. It'll match, it'll be the same variable as what's in your summand. And it's giving us the lower limit. That's where we start. That's the starting value. And then the upper limit is the ending value. That's where we would stop. Okay. All right, so here's a few examples. All right, so the sum of k squared for k equal to 1 to k equal to 5 looks like the sigma notation on the right there. Okay, so we have k squared. 1 is where we start. 5 would be the ending value. In summation notation, this is what we would be adding up. So 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. Okay. All right, so the second one, the sum of 1 over k for k equals 3 to k equals 5 is what's shown on the right. Okay. So it's telling us that 3 is where we start, 7 is where we stop, and the formula we're using is k to the negative 1 or 1 over k. Right, so in summation notation, so this is the second one here, I just put a check mark by. We would start with 3, so we would be plugging in 3 into 1 over k, so we would have 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7. So that's what the sum would be in summation notation. In other words, summation notation is what are the values we're going to be adding up once we do the substitution. Right, so on the third one there, we have on the right-hand side, we have the formula. In summation notation, we have the formula for, in sigma notation, we have the formula for k equals 3 to k equals 7, the sum of 2 to the jth power for j equals 0 to j equals 5. That's telling us that we're going to start with 0, we're going to end with 5, and the formula we're using is 2 to the j. I have to say, when I'm reading these, it's easy to look at the wrong thing because they're over more than one row and there's no capitals in it. So I'm going to do that so I don't read the wrong row again. There we go. All right, so what we would be adding up is 2 to the 0, because that's where we're going to start, because we have j equals 0 as our lower limit. Plus 2 to the first, plus 2 squared, plus 2 cubed, plus 2 to the fourth, plus 2 to the fifth. And then, so we've gone through 1, 2, and 3. The final one there is the sum of a sub I for I equals 2 to I equals 7. So that tells us what our starting and ending values are, and we have just a variable expression, a to the I. So we would have a subscript 2 plus a subscript 3 plus a subscript 4 plus a subscript 5 plus a subscript 6 plus a subscript 7 in summation notation. That's a tongue twister. So we've gone through all 4. So let's look at the one above. In summation notation, okay, that would be equal to, so we're starting off with 2. 2 is our lower limit. 3 times 2 plus 1. And 3 times, and I'm just going to put parentheses around it. So that's the first term. 3 times 3, oops, plus 1. That's the second term. And 3 times 4 plus 1. And can't really squeeze them in here, so I'll just write them underneath. And then 3 times 5 plus 1. So that's what that's what our sum would be in summation notation. And then we could also just find the sum by calculating out the values out. Okay? So it's a pretty easy one. I think I don't have to go over this one in terms of finding the sum here. We'll go over some harder ones for the sum. Right, so on the next page are some examples I was going to have you do for whiteboard practice to just write out the sums. Right? I think I'll just go over these ones with you, and then maybe I'll give you some other problems in the next section to find the sum of. All right, so here we have the sum of k cubed, starting with k equals 1, and then our upper limit is k equals 5. So in summation notation, this would just be 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed. Okay? That's what it would be in summation notation. All right, so for the second one there, we have -1 to the j power times, it looks like 1 over j. Where our starting value is our 2, it's our lower limit, and our upper limit is 7. And so in summation notation, we would have -1 to the second power, 1 over 2. That would be the first one. I'll just put parentheses around the whole thing. Plus, of course, there's quite a few of these to write down, huh? -1 squared, cubed, third term, cubed times 1 over 3 plus -1 to the fourth, 1 over 4 plus -1 to the fifth, 1 over 5, and I wish there was only 5 terms because I'm out of space here. So I'm just going to make these parentheses a little smaller so I can squeeze in the last values underneath here. And then plus, we just keep on going here, -1 to the 6, 1 over 6. And finally, -1 to the 7th, 1 over 7. All right, so it would just be the sum of all of those values. If we want to find the sum, we would just calculate and add up the values. In summation notation, that's just showing what values we're using for our sum. And then finally, the last one there would be the sum of the values for 2m plus 1 with the lower limit of 0 and then all the way to our upper limit of 4. So this would be 2 times 0 plus 1 plus 2 times 1 plus 1 plus 2 squared plus 1 plus, I'll write it over here, 2 times 3, did I say 2 squared plus 1? 2 times 2 plus 1, and 2 times 3 plus 1, and 2 times 4 plus 1. There we go. All right, so that's what it would be in summation notation. We're just writing the values out. Okay? It's not asking us to calculate it. So I hope that was okay. That was clear for you. What summation notation means, it just means to write the values that, just plug the values into the rule and write those down. Here are some selected rules for sigma, and I'm highlighting, I think there's 6 of them, because they're useful. So the first one, we have sigma, and C is a constant. A subscript K is just some rule that we're plugging our values into. So essentially we're using some rule and we're getting a first value and a second value and a third value and so forth. And K equals 1 is the starting value, and N is whatever number of values there are. Okay? So N is whatever number you want it to be in these formulas because it's good for any number. And all that first rule is really saying is that you could either, for each value, multiply by this constant. So, say you had, let's just say, the constant here is 5, right? And let's just say the terms were, for our sum here, were, so let's just say A1 was 1, and the second term was 2, and the third term is 3. All right, let's just say there's n equals 3. Okay? We could either, for each one, take each value, so the sum would be, so in this case, the sum would just be 5 times 1 plus 5 times 2 plus 5 times 3, and that would be 5 plus 10 plus 15, which would be 30. Okay? So in other words, we could solve it like the first way, where we've got the 5, on our part as part of our rule there, and for each of the values, once we plug them in, we then calculate and multiply by 5. Or we could take the 5 and put it in front. So instead of multiplying each one by 5, just get the sum and then multiply the whole thing by 5. So in this case, we would have 5 times the sum, and so our sum was 1 plus 2 plus 3. So that would be 5 times, and that would be 6, and we get 30. And that was the exact same thing we did with the rectangles, right? With the Riemann sums, right? We didn't multiply each of the rectangles times the width, the change in x. We just found all the heights and then multiplied one time by the change in x. And that's what that first rule is really telling you. You can find the sums and then multiply by a constant, or you could multiply each term. You could multiply by that constant. Either way, you'd get the exact same answer. Okay, so you can factor out constants. Okay? The second rule is telling you that the sum where C is a constant here, where we have some number of terms, is just the constant times the number of terms. So if I'm finding in other words, so this was just explaining number 1, explaining number 2 here. So let's just say our constant is, let's just say this is, well, why not? We'll do 4. Different number up here. K equals 1, and let's do 3. Okay? So what's going to happen here is I'm just adding 4 3 times. 4 plus 4 plus 4. I've got 3 4s, right? There's nothing to plug into. So my first term is 4, my second term is 4, and my third term is 4. Right? There's not a place to plug in a variable. It's just 3 4s. So our sum is 12. Okay. So if you're finding the sum of a certain number of the same constant over and over again, you don't have to write down however many n is times 4 is going to be your sum, okay? Because you're just going to have that same sum added up again. So it's just showing repeated addition, because that's what it's going to be if it's a constant value you keep adding up as multiplication. Okay, that's all that second rule says. And then the third rule says if we're finding the sum of a sum or difference, we can take the sum or difference and find this value and then add them all up, or we can find the sum of the first one and then the sum of the second one and then add or subtract depending on what the rule was. Okay? So we could do a really, really simple one here. So we'll just keep starting off with 1. And let's just say n is 3. Okay? And we'll make this nice and simple here. So the a subscript k is going to be 2x, and the b subscript x squared. Okay? All right, so we've got the 3 values there. So I'd have 2 times 1. And it'll be plus, right? So my rule is going to be, I probably should write my rule out. I didn't give you a plus or minus. So my whole rule here will be 2x plus x squared. Okay? That'll be our rule. Okay? So I could either find 2 times 1 plus 1 squared, and 2 times 2 plus 2 squared, and 2 times 3 plus 3 squared, which would give us 3 plus, this would be 4 plus 4, 8, and that would be 6 plus 9, 15, and so that would be 26. Okay, I could do it that way, or instead I could do the sum from k equals 1 to 3 of the 2x, and then the sum k equals 1 to 3 of x squared. Find them each separately and add them up. And you can see you're just adding up the same values, just kind of doing it in a different order. So that would be 2 times 1 plus 2 times 2 plus 2 times 3 plus 1 squared plus 2 squared plus 3 squared. And so that would be 2 plus 4 plus 6, so that's going to be 11. And then 1 plus 4 plus 9 is going to be, wait, did I add up somebody incorrectly? 9 and 4, 13, 14, oops, I think I forgot somebody here. 6, 4, 10, oops, 12. I don't know who I said wrong, but I wrote 11 and it should be 12. Right? And then this would be 1 plus 4 plus 9, which is going to be 14, and that would be 26. Now you might think, what difference does it make? You're doing the same things. You're just doing, doing either you're doing it all together, or you're doing all of the 2 multiplying by 2 and then all the squaring together. Well, it might make a difference because sometimes it might be easier to calculate it out, because maybe there's a shortcut, a little formula we could use to calculate one of those out and make things a little easier for us. So that's why it might matter that we could either do it all together, or we could take care of each part of this separately, okay? Each sum separately. So I could find the sum for the 2x's and then find the sum for the x squareds. Okay? That's all that third rule is saying. Okay? All right. So the next 2 or 3 rules are just handy-dandy formulas, and we're not going to go about proving them. Someone has done the long, hard work for us of finding another way to find a sum. And so you have 2 ways that you could find the first n integers. So here, k is a variable, so in other words, let's say n was 10. That would mean you were adding up for this first one here. Okay? So if it were this, k equals 1, and this is 10, you're adding up the first 10 numbers. So that would be 1 plus 2 plus 3 plus 4 plus 5 plus 6 and plus 7 plus 8 plus 9 plus 10. You stop at 10. Okay? All right, so no big deal if it's 10 numbers or 5 numbers or something like that. But what if it's 10,000 numbers or 1,000,000 numbers? Well, I'm going to get sick of writing them and sick of adding them up. Okay? So there's just a formula we could use to find the exact same sum. Okay? So that formula, I would just substitute the upper limit here. So this is for the first n integers. So it does mean that the lower limit equals 1. Okay? If you're starting at something other than 1, then you're going to have to do something a little creative to be able to use this formula. Like start at 1 and then subtract the first term or something. If you were starting at 2. That's how you could be creative. But if I wanted to add up these first, say, 10 integers, instead of adding those 10 numbers up, I could use the formula and get the same number. So my upper limit here is 10. This would be 10 times 10 plus 1 divided by 2. Right? So that's going to be 10 times 11 divided by 2, and I can cancel that out, and that's 55. So if you don't believe me that that's the answer, you can add up 1 plus 2 plus 3 plus 4 plus 5 and so forth and see, is it 55? And assuming I didn't make a math error, which I don't think I did on this one, you'll get the exact same answer as I got. Okay? So it's very nice way to add up this formula, a lot of numbers, much more efficiently. Okay? With a lot less stress. But you do have to start with k equals 1. Okay? It won't work if k equals 2 or k equals anything else. However, if it was k equals 2, we could get the sum and then find k equals 1 and subtract it. And then we could use the same formula. All right, so if you didn't think that for adding the first 10 values was too bad, maybe you wouldn't want to add the first 10 squares, right? So here we have a formula. So rather than adding 1 squared and 2 squared and 3 squared and like having to square all these numbers and then add them and dot, 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 dot to all the way to 10 squared. Okay, so we're just saying in this case n equals 10. We'll just use n equals 10 again. So I'm just going to do 10, k equals 1, x squared. So I'm going to add up the first 10 squares. All right. So instead of having to square and add up all those numbers, I could use this formula here. And it's really nice if it wasn't just 10 numbers, it was 1,000 numbers, because I'd really going to get tired of that. All right. So another way we could calculate out the same sum, right, is if we want the first 10 squares, we'd take 10 times 10 plus 1 times 2 times 10 plus 1. Okay? All divided by 6. And so the sum of the first 10 squares then would be 10 times 11 times 21, and then we just have to multiply, divided by 6, excuse me, divided by 6, and then we just have to multiply those together. And actually, I'm going to reduce here, so I can divide 6 into 21. They're both divisible by 3, so this would be a 7, and so now this would be a 2, right? But I could do that as well. Okay. So now it'd be 35 times 11, which is going to be 350 plus another 35, so 385, right? So our sum here would be 385. So it's just a shortcut. Someone took the time to find you a little shortcut here for adding up a whole lot of numbers. And then the first n cubes, right? If let's again just keep with 10. So if we wanted to add up the first 10 cubes, we could, add up 1 cubed and 2 cubed and 3 cubed all the way till we got to 10 cubed and add those all up. Or a little shorter, we can use a little formula here. And we can find the same value simply by taking 10 times 10 plus 1, all divided by 2, and squaring it. And this will give us the sum of the first 10 cubes. So pretty nice. So I'm going to reduce. So that's going to be a 5 now. So I've got 5, this is 11, right? So this is going to be 55 squared, which I don't know off the top of my head. However, I could just grab a calculator and we could find that value out. I don't have a calculator anywhere near me. My microphone only stretches so far. So you can calculate out that sum by taking 55 squared. But notice how that was hardly any work at all as compared to having to add up the first 10 cubes. Okay? So these are just some nice formulas. They're provided in your notes for you, and they're just some shortcuts. Okay? All right, so these were going to be whiteboard practice problems. It wouldn't be a bad idea to check yourself and see if you got the right answer. Oh, look at that. I happened to choose the same number. Well, I forgot what problem was over here. Well, we have actually just done that first one because I happened to choose 10, and we already know it's 55. As a matter of fact, you can see if I move my key here. Come on, page. There we go. It was 55, all right? But we could also add up, say, the first 20, right? The first 20 terms, right? And maybe you don't want to write down 1 plus 2 plus 3 plus 4 plus 5. So instead, you can use this nice formula here, and we've got 20 times 20 plus 1 divided by 2 is going to give us the sum of the terms. And it kind of makes sense. We're taking kind of an average. It's going to be, if you actually were to pair, another way to add up numbers very quickly is to pair the first and the last and then add up the number, whatever that sum is, times half of the numbers you have. This kind of uses that same idea, only a much shorter little formula here. So we have 20 times 21 divided by 2, and not much in the math there because it's 210. So that would be the sum of the first 20 integers. Right? So that formula comes in handy. So really in this whiteboard practice, I was just testing your knowledge of being able to, here's a formula, and I even gave you a hint because I provided the formula. I think there's like 4 examples here, and I think that's all I have on this. All right, so here we want the first 6 terms. We have a formula here, negative k squared. All right, so you could, one way you could do this is to have negative 1 squared and negative 2 squared and negative 3 squared all the way till you got to negative 6 squared. Notice the negative's not being squared. Or we could use this formula as a little bit of assistance here. Now, if you notice, there's a common constant here, right? We have a c equals negative 1. So one thing we could do is factor that out, right? So we have the negative 1 in front, and then we're finding the sum of these 6 terms, and now we do just have k squared. Okay? So we could, to find the sum of the first 6 integers squared, we could use the formula down here, and then we'll just multiply by negative 1. So it would be, I need some space here, right below it. The big box there, by the way, has the answer. Negative 1, and we would have then the rest of this would be, n was 6 here. So we have 6 times 6 plus 1 times 2 times 6 plus 1. Missing a parentheses there. And then all divided by 6. Right, so now I think I have all my parentheses in the right space, so I'm not multiplying anything I didn't intend to. Yeah. All right, so then that would be negative 1 times. We have 6 times 7, and that would be 13, all divided by 6. Okay. And makes quite a bit of sense to cancel out the 6. So it would be negative 1 times 7 times 13. And that would be negative 91, right? Hopefully. Ah, good thing. The answer is correct. Wouldn't want to have the wrong answer up here. All right, so that we have the correct answer. All right, let's do, maybe I got, what do I have, like 2 more? And so this one, we want the first 100 terms minus the first 99th terms. Okay? So what if we calculate that out? Okay. So we could use our handy little formula there. All right, so the first 100 terms, all right, is going to be 100. So our first term, and then 100, or 100 plus 1, right? Because that's our n. Our n is 100 for the first one. And then all squared, parentheses around that, and then divided by 2. And then we're subtracting from that. I don't have much space here. I need to move this. Maybe this wouldn't mind being out of my way. Whoop. There we go. You look at that for a while. I need more space. And then 99. So 99 times 99 plus 1 squared divided by 2. Now, that's one way we could do that, right? Certainly better than plugging in 100 terms. And we could simplify that. So this would reduce to 50. And even if there were shorter ways than this, it don't matter. We could just use a calculator to do the rest of this, couldn't we? And it wouldn't take us very long at all, because it would just be 50 times 101 squared minus, and it'd be nice if this one reduced, but it doesn't until after we square. 99 times 100 squared divided by 2. And I grabbed a calculator this time. 101. So that first term there is 510050. And then the second term there is 495000. So our final sum is just going to be, well, if I add another 5,000 here, that would be 500,000. So it looks like it's going to be 15,050. It's really late, so I'm really tired. I'm just going to double check my subtraction at the calculator. Oops, well, it doesn't help if you leave out a 0, does it? 5. Yes, 15,050. I just didn't. When you get tired, sometimes you make silly little errors, and I didn't trust my math. So that would be our answer. Let's see if we get the same thing over here. Wait. Oh, I forgot to multiply. Did I forget to multiply? My values are correct. Oh, drat, the square's on the outside. Oops. Well, it doesn't help if you make an error. I told you I don't trust my math today. I forgot to put when I was writing it down, I wrote the square in the right spot, but then I wrote it on my second step here, and I completely forgot to keep the parentheses. I have to multiply first and then square, which means, by the way, the 2, I could reduce this one, but I forgot to square here. So, if you forget the importance of, if you forget to put your parentheses in the right spot, and on the second one, I forgot to put it in the right spot altogether. I told you I was tired. So, we had to square first. So, if we squared first, then we would have this number, instead of squaring one of them and only multiplying, minus this number, which would give us 1,000,000, which is a lot easier subtraction too. All right, so make sure when you use the formulas that you don't forget your parentheses. I just completely forgot one of my parentheses and then messed up something very important. All right, so we all make mistakes. But other than that, this wasn't a hard problem, as long as you put the parentheses in the right spot. I'd make this video again without that mistake, but it's getting late, and I'm tired. All right, so we're going to solve the following here. So here, we don't have any pretty little rule. We would just plug in. There's not a shortcut. So our sum, we would start with 1, would be, and we'd have 1 times 1 minus 5, and 2 times 2 minus 5, and 3 times 3 minus 5, and 4 times 4 minus 5, and 5 times 5 minus 5. So our sum would be negative 4 plus 2 times, that would be negative 3. So that would just be negative 6, right? This would be negative 2 times 3, so that would still be negative 6. This would be a negative 4. Very kind of interesting, huh? And then this would just be a 0. So it should be negative 20. I'm afraid to move this thing. Yes, it is negative 20. Okay. So I didn't really have you do this on whiteboards because I think they're straightforward. I mean, they're just some, being able to understand, what the summation notation tells you, and then just being able to use a few formulas when it might be helpful. And so I'm going to end this lesson with just kind of recapping on some things about approximating area using rectangles. So the effect of the number of rectangles used in the approximation. So the difference in the approximations when using different number of rectangles. So if we use 2 rectangles compared to 8 rectangles, which is why I changed the classwork, the homework, the assignment I gave you, well, the homework really, from 8 to 2, is because 2 is going to have a whole lot of error here. With only 2 rectangles, look at all that extra space. Where we have 8 rectangles, even though there's 8 little triangular pieces there, they're a lot smaller than the 2 triangular pieces here on the other one. So as we increase the number of rectangles, we can look at what happens. Okay, so using more rectangles will give us a more accurate approximation of the area under the graph. So 8's better than 2, and 100 would be better than 8. So here, a little visual example. So here we're finding the area under the curve. I don't have the equation written down anywhere here, but that's okay. But here, what's the important thing is the number of rectangles. So the first one, we have 10 rectangles, and these are all right and left Riemann sums. So we have a right and a left. On the upper 3 are the right Riemann sums, the lower 3 are the left Riemann sums, and so you can see the area. So for 10 rectangles, the right Riemann sum was 0.385. For 10 rectangles, the left Riemann sum was 0.285. For 30 rectangles, the right Riemann sum was 0.3502, and then for the left Riemann sum was 0.3169. Okay? So interestingly, they're getting closer together. The left is getting a little larger because there's less, it's less of an underestimate, and the right is getting a little smaller. It's less of an overestimate. And then with 50 rectangles, they're even closer. We've got the right Riemann sum at 0.3434 and the left Riemann sum at 0.3234. So what if we put in more rectangles and more rectangles? We get closer and closer to being the area. And so my final thought, and this video was longer than I thought it would be, sorry for that. As the number of subintervals increases indefinitely, the Riemann sums approach a limiting value, which is the area under the graph. So we're going to look a little bit at limits in the next lesson, and maybe we'll use some of this summation notation to help us calculate some of those things out. All right, so bye for now. Hope you enjoyed this podcast, and I hope that if you had any questions on summation notation, that at least the notation is a little clearer for you. Okay, all right, bye.